Hello, this is Michael Davies from Space Dust Studios. In this video, I'm going to give you a whirlwind tour of our custom vehicle physics implementation for our party combat racer Space Dust Racing, which is coming in 2015 for PC and consoles. We're using Unreal Engine 4, but I'm not going to get into any code, blueprints or formulas. This is really just an overview of the general principles that we're using, and you can use the same approach within Unity 3D or any other game engine that has a physics component. I'm assuming some basic knowledge of physics engine principles, so velocity, forces, torques, raycasts, and also some basic knowledge of 3D coordinate spaces, vectors, and so on. To start off, let's talk about the requirements for Space Dust Racing. We're aiming for fairly low detail arcade physics, not high detail simulation like you'd find in Gran Turismo. We want bouncy suspension, we want the ability to flip and roll vehicles, and the ability to crash into other vehicles and ram them off the road. We don't want to get bogged down in complex traction simulation or gear ratios or forward wheel drive or rear wheel drive support. Generally just putting too much detail into the individual wheel simulations, because some of our vehicles might not have wheels, they might hover or they might have tank treads, and we want the same physics for all of them regardless of how they look for gameplay balancing reasons. We want the ability to toggle the physics on and off at any point. For example, making the vehicle perform a canned animation like a winning dance. And we also want the ability to change the physics completely in certain states, like spinning out in oil slicks. We're not using Unreal Engine 4's inbuilt vehicle physics, as this is a bit too simulation oriented for our needs. And it's not easy to override, or in other words, hack to pieces, which is what we're going to do. So let's start out with a simple physics box primitive. This is going to be our basic collision proxy for the vehicle, the thing that'll hit the world and other vehicles. This could easily be a custom physics mesh, a capsule, a sphere, a compound of multiple primitives, whatever fits around your vehicle's visual geometry the best. We'll add the visual component later on. For now, since this vehicle is just a lump, I've hooked up a debug button to flip it by applying a physics impulse, and now we can just see how it reacts when it lands on the ground. Pretty exciting stuff so far. Now let's add some suspension to the bottom corners of this box, so it's pushing itself up off the ground, just like actual wheels would. To do this, every frame we perform a raycast from each bottom corner of the box, so the front left, the front right, the back left, the back right, going downwards in the local vehicle space for the length of the suspension. So in Space Dust Racing, it's about 60 centimeters for us. Let's focus on one raycast for a second. If this raycast doesn't hit anything, then the suspension is fully extended, and so we don't need to do anything. We can let the physics continue simulating. But if it hits something, we can calculate the compression ratio of that suspension as a number between 0 and 1. So 0 means it's fully extended, it hasn't hit anything, and 1 means it's fully compressed, so it's at the absolute compression, so the hit point is exactly where it started the raycast. Then all we need to do is add an upward force on the box at the appropriate position using the physics engine. We scale this upward force by the compression ratio, so basically more force acts on the vehicle as the suspension compresses more. Now when you look at all four raycasts doing this work together, you get this great bouncy suspension effect, and it keeps the vehicle elevated off the ground. One side note, for each raycast that hits something, we'll make sure to remember the compression ratio for that suspension, the surface impact point, and also the surface impact normal, and these are results of the raycast. We'll use them later on to help us figure more stuff out. We're off to a kind of cool bouncy start, but we still can't accelerate or brake. So to fix this, whenever the accelerate button is pressed, we apply a forward force to the vehicle. Braking is just the same thing with a negative force. When you're finding the vehicle's forward direction, it's best to project it onto the road plane, which stops a vehicle from launching off the ground if it's tilting upwards a little bit, or pushing into the ground if it's tilting down. And because we remembered the impact details from those raycasts earlier on, we already have the information we need to calculate all this stuff. Another simple trick is to add the accelerating braking force at a slightly lowered position from the center of mass towards the front of the vehicle. And this makes the vehicle tilt backwards and forwards as you accelerate and brake, just like a real car would. It's very easy to overdo though, so you have to tune it to get it feeling about right. Now we need to make this thing turn based on the left-right turning amount from the input device. This is a little bit more interesting. The naive approach here might be to simply bypass the physics engine and just rotate the vehicle around its up axis each frame. But this skips around the physics solver, which will lead to glitches when collisions happen. And the proper way to do this for a physics-based approach is to apply a torque instead and let the physics engine do all of the rotating for us. This ensures that if the vehicle's obstructed, maybe there's a wall in the way or another vehicle, it'll react appropriately and not glitch out. The basics of the vehicle controls are in now, but we've still got no traction. And as you can see, we're slipping and sliding all over the place. That's kind of fun for a drifting mechanic or driving on ice, but we need to get control over it so we can decide on the amount of slip applied to the vehicle, maybe based on the surface or the road type. To fix this, each frame we can find the local sideways component of the vehicle's velocity and apply a force to the vehicle in the opposite direction, scaled by some factor that feels good to us. This makes the vehicle grip the road better, and we can play with this value to simulate all the different road surfaces we want, from ice to concrete. There's one final tweak we can make to keep the vehicle upright more often, and that's to lower the centre of mass to be beneath the vehicle. Now, this is totally fudged and not realistic, but it makes the vehicle act like an inflatable punching bag with a really heavy bottom and a light top. And the effect of this is the vehicle always wants to roll back upright. You'll see this effect in many off-road driving games where it's important that the player can flip their vehicle, but you still want to ensure that they can roll back on their wheels most of the time so that they stay in control, because it's a bit more fun and a bit more forgiving. In Space Dust Racing, we use this hack for vehicles while they're alive, but for dead vehicles, we put the centre of mass back into the centre of the object so that they'll tumble and roll more easily, and it just looks a bit more fun that way. Essentially what we've done here is just a series of hacks to make our box feel like a vehicle, and now we can just drop a visual mesh on top for the chassis and the same for the wheels. For the wheels, to find out where they should be relative to the chassis, we can use the suspension raycast information we gathered earlier because we have the distance there. We can also reflect the turning input on the wheels, and that's done by just rotating them left-right by the amount of controller input turning amount with a little bit of smoothing. This is what it all looks like in action. You can see the big advantage of using physics to drive your vehicle movement is that you can now use physics impulses from explosions and crashes to throw your vehicles around, and the physics does all of the hard work for you to make it look cool and give you these exciting moments. With physics though, the devil is definitely in the details, and it does take quite some time to tune properties like friction, restitution, and also balance forces and torques against each other to feel good, because everything affects everything else. But with small adjustments and lots of playtesting, the results are definitely worth it. So that's it. I hope you found this video interesting. If you have any questions or feedback, you can leave a comment on our dev blog or email me directly. Please subscribe to our channel if you'd like to see more videos like these, and thank you for watching.